beginning of last session, I mentioned that the machine learning tasks in general are divided into two groups of unsupervised and supervised tasks. But for graphs, this is just more than that, because we don't have only data sets that try to learn something based off of different graphs. They different basically data. We also have problems that we deal with within the graph. They basically a question, basically a task that we want to solve within a single graph. So, but the graph level tasks are essentially a natural equivalent of the problems supervised and supervised that we deal with in the basically data that is residing on Euclidean basically domain. Two examples. One is graph regression, where, for example, you have multiple a data set of graphs, different graphs, like molecules, for example, and you want to predict a real value for each of these, like a chemical property of this molecule. And for these problems, your data set is essentially a set of molecular graphs. We show them with G and their corresponding labels. So you have, for example, N graphs, N labels, and you want to learn a function, essentially, that maps from each graph in the test set to its corresponding data. Now, that's the case in the graph regression. And in graph classification, we have problems that we want to find one of the two categories for graphs. Like, for example, the test of toxicity. We want to predict if a particular graph that we are dealing with is toxic or not. We train it. There are two labels associated with each graph during training, and that class is going to be our label. Now, the difference between this type of classification and, for instance, node classification, where we were trying to classify if nodes that were representing users in a, for example, Twitter network were fake or not. So that was a type of classification as well. So the difference between these two is that in that case, in this case, essentially, we can look at our data set and we can assume that each graph is an independent data. We have IID data and we are trying to train our model. But when we look at the classification case in among nodes, that's not the case. The nodes that are connected to each other, we can't assume that these are independent. And we're actually trying to use the structure of the graph, those connections that exist between these nodes, to leverage and solve the classification problem in that situation. But when we have a data set of single graphs and multiple of basically graphs, we have thousands of graphs, and each of these is looked at as a single data point, which is independent from any other graph in the data set. So we also have graph clustering problem in which is equivalent to the unsupervised problem that we were dealing with in regular, just your normal everyday machine learning. I mentioned an example of the case of categorizing labels in MNIST dataset. And here, for example, we can use the same ideology to classify, to find clusters of molecules. And that would basically be based off of their inherent properties. Like, for instance, let's say that we have this bunch of molecules and they can have different type of connections, different rings, different properties. For instance, we can basically find our algorithm to, and we can basically see after whatever it did, we can see that it has categorized molecules that have larger rings, basically, for example, rings of size 8, together in one cluster, the ones that don't have rings in another cluster, and so on and so forth. So this is a latent inherent characteristic of that graph. We are not dictating what the unsupervised learning algorithm should do.